so in this video I'm going to be introducing you to the idea of base 12 geometry and the Dozenal Cartesian plane, or the base 12 Cartesian plane. And I'm going to be introducing you to the beginning of the geometric pattern, the sort of underlying structure of the geometric pattern that enables us to divide the circle perfectly into 360 degrees. And from that basis, once we understand that structure of that diagram, we will be able to go deeper into the geometry of the circle and eventually encounter the base 12 version of pi, which emerges from the geometry of the circle that we are discovering on the base 12 Cartesian plane. So we're just going to start on the base 10 Cartesian plane. You can see I've drawn a line here that has the length of 0.5 root 2 in base 10. So we are working in the size of decimals. Okay, so decimal, just quickly, DEC, that's the derivative of, I think the word decimus in Latin means a tenth. So decimals is in base 10. And the real difference between base 10 and base 12 is that we're dividing the length of 1 into twelfths in base 12 instead of tenths as we do in base 10. So a normal 1 by 1 square is further divided into tens in base 10. If you were to hand somebody a piece of graph paper and say, hey, draw a 1 by 1 square, outline it, you would just naturally go over 10 little squares and up 10 little squares and make that square and say, well, there you go, that's a 1 by 1 square. Not even really thinking about the fact that that's a base 10 1 by 1 square, and in another base it would look a little bit different. Okay, so that's basically it. We're going to do the same thing in base 12. Draw that 0.5 root 2 length line in that same position in relation to the sides of that square, and we're going to see what happens when we do that. All right, so now we're looking at the base 12 version of that 1 by 1 square. So this is a Dozenal square, or it's been divided into dozens instead of decimals. It's dozenals, I think. And so that means that each of these little squares is 1/12 of the entire length of 1. So we go 12 by 12. So again, if we were thinking of a culture that started in base 12 and they were handing each other pieces of graph paper and saying, hey, draw a 1 by 1 square, they would naturally draw it 12 by 12. And that 1 by 1 square wouldn't be bigger than a 1 by 1 square in base 10. They'd be exactly the same size. The length of 1 is the same, but we're dividing it up into smaller units. So 1/12 is a smaller unit than 1/10. So here I've also drawn I've gone up the length here of 0.7, then across here, 1, 2, 3, 4, 5, and we have a length of 0.5 root 2 in base 12. So from a base 10 perspective, that length is 5/12 of root 2. If we drew a line all the way across here, that would be one complete length of square root of 2. And so 5 little squares is 5/12 of that on this Cartesian plane, or the Dozenal version of the Cartesian plane. Okay, so we're going to go a little bit farther now with this one line. We're going to draw a line that connects from the point 0, 0 here up to that point. So the coordinates of this point, the x coordinate is 1, and the y coordinate is 0.7, and this one here is reversed. The x coordinate is 0.7 and the y is 1. So when we draw these lines going from here to those points, the slope of this line is rise over run. So we have a rise of 1, then a run of 0.7, or a rise of 0.7 and a run of 1. Okay, so those are the slopes of these lines. So we get this long sort of triangular shape. And now we can also connect the points, because what we want to remember is that because we've gone over the length of 1 and up the length of 0.7, because it's the length of 1, we can also go over the length of 0.1 and up 0.07. So actually any point along the x-axis is going to have a corresponding coordinate, a corresponding y coordinate. And the same thing here, as we go up the y-axis, any coordinate or any point on the y-axis is going to have a corresponding x coordinate with these dimensions. So we can also go along here and we can connect these 2 points and have a little line here that is the length of 0.05 root 2. So this next line here is going to have a length that's 2 times 0.05 root 2. And then this line is going to be 3 times that length, then 4, 5, 6, 7, 8, 9, dec, L, and then do for a dozen, or 12. We multiply 0.05 root 2 by a dozen. That's what a dozen looks like. And then we get 0.5 root 2, which again is the length of that line. So this is the very simple beginnings of the diagram that is going to enable us to divide the circle into 360 perfect sections. And so I just want to basically stop there for this video and let you just absorb the fact that this is a very simple diagram. It's very simple, and yet it's very anchored on the base 12 Cartesian plane in a way that it can't be in base 10. It doesn't line up the same way. We already looked at it in base 10. You can kind of see it here. My camera isn't going to allow me to look over there, but I think you know. But 0.5 in base 10 is halfway up the side, and going across it cuts that same square differently. So we're going to just stick to the base 12 Cartesian plane. I don't want to keep going back and forth. We just want to start here and then keep growing and expanding this geometric pattern. In the next video, we're going to look at the relationship of this triangle and this triangle here to the other very foundational geometric patterns that we're already familiar with, which is the 30-degree triangle and then the 45-degree line. What's the relationship of those foundational geometric elements to this new and yet also foundational geometric element? So I just want to introduce one last time before we go that I have written a book all about this already called Understanding Base 12 Math, How to Draw the Perfect Circle Using Dozenal Geometry. I introduced this geometric pattern in this book. I'll go all the way through, show you how to draw the diagram for 360 degrees, and then we do the equation, which is sort of built into this geometry. We have a diameter and a circumference of sorts, and we can do that geometry. We get some interesting numbers. All that information is in this book. I don't even want to mention the big, well, it's pi. I think there's a base 12 version of pi that emerges from this geometry that is different in base 10. And I think it is the correct version of pi. So I'm just going to say it. It's in this book. You can order it from Amazon if you want to get ahead of the game. If you're not quite ready to do that, just follow me. I think another link to the next video should pop up. If it doesn't, I haven't made the video yet. But that's what's coming. Dozenal pi. And this is the very simple foundational geometric pattern from which the whole diagram grows. This is the seed right here, and you can see how it's very, very simple to draw.